Okay, so today I'm going to talk about marking streets to improve parking density. This is joint work with Steven Skinner. So today I'm going to talk about a problem that's specific to New York City. It could be useful for other cities too, but it raised from New York City. So in New York City, there's this idea of alternate side parking. This is because on the street, on each side, there are two 1.5-hour intervals each week where the street sweepers use one side of the street. And when that happens, cars cannot park there. And yeah, so this will be one of those examples. This gives some very interesting parking dynamics. So at the start of the forbidden time intervals, the entire side of the street becomes empty. All the cars must leave. And then the drivers basically just double park on the other side of the street and are waiting for the street sweeper to go through or wait for the time to run out. And so this is a picture of something in effect. So here's a street sweeper just going through, and then all the cars are just double parked. And once the street sweeper goes through, the cars will just all park at the same time, almost the same time, basically. And then afterward, the entire side of the street becomes full. So the reason we think about this problem is because space is scarce. And so you can notice in New York City, all the streets does not have any parking markings. But in those parking lots, there are all kind of markings. So question is, can we add markings on the street to improve the parking density? So on the street, there's a larger variance on length than just width. So in parking lots, width is usually the problem. And also the markings can only be an optional visual cue. Like if you just go into New York City and say, now we're gonna force everyone to park inside this particular block, yeah, the people will go crazy about this. So the question is, can we have markings on the street to improve the parking density? And if so, how far apart should the markings be? So as for the previous work, one thing is different cities obviously have different rules on parking, but all of them just have to meet the American Disability Act. So there are certain cities where they enforce on street parking with markings. For example, the city of Bowling Green in Kentucky. We did not find that many cities with this property. And in terms of research, there's a paper back in 1958 by Zheng. It's about a one-dimensional problem concerned random space filling. So the idea is you have an interval, and then you have inter-unit intervals coming in randomly, and eventually it stops because there's no coming in randomly because there's no space left, and you want to know when the process stops how many intervals there are. So this is a completely theoretical problem, which is close to what we are doing because the intervals are just cars. And then there's also a study for different strategies for select parking spaces, but this is mostly for parking lots instead of on-street parking. So we are considering, can we improve the parking density through different incentives? So let's say there are no incentive where all the cars are parked randomly. It might look like the cars on the top. And we could choose different strategies. We could educate the drivers with a campaign to increase drivers to kiss the bumper, which means reduce the distance between themselves and their neighbors. Another one would be the one we are suggesting is to paint appropriate spaced markings on the street. Then we want to encourage the drivers to hit the line. They don't have to, but we do encourage them to. So, and because the lines are the natural, drivers will naturally try to hit these lines because now they have a visual cue. Um, and we increase the parking density by having well-spaced markings, which forces the remaining driver to use tight spaces. So let's say, for example, the picture on the bottom. So you have the two markings, and if you have a car that hits the markings, car 1 and car 2, then the third car has to go in between, which takes up a very small space. So the model we are considering is driver comes in one by one. So a driver will pick a parking space with probability alpha. And then it uses the kiss the bumper strategy or hit the line strategy, depending on what we are trying to do. And the remaining probability will just park randomly, which means just find a random space and park there uniformly on the line. Once the driver parks there, the next driver comes and repeat the process. And the process stops when there's no car can fit anywhere. So here's an example. So this will be a representative view of the behavior of different strategies. On top is a random parking strategy, where cars just come in and park randomly. On the middle, it's a kiss the bumper strategy. So there are certain cars that will try to park as closely as possible to other cars. And finally, then there's a hit the line model, where we actually drew markings of size exactly 2 units if we consider all the car have unit 1. And as you can see, some of the cars here, for example, maybe this one, it's forced into this position because there's a car in front and the end are hitting the lines. So one thing we did study is to compare the parking density, compare with what's the probability a driver decide to use a strategy. And so we actually call this alpha the compliance ratio. So when we have the marker have exactly 2 units apart, and all the cars are 1 unit, and depending on this compliance ratio, this is the graph of it versus the parking density. So at some point, hit the line actually does better than kiss the bumper, and this is because the hit the line start to force more and more drivers to go into those created spaces. Yeah. Of course, what we really want is to run a real life model on it. So a real life model is more complicated than a toy one. So we will first use the real life car distribution. So we use the car day sales data of the top 7 car companies, which account for 85% of the car sales. And the average length of the cars is around 194.4 inches. This number might be useful later on. So we notice the street length is going to be bounded by around 200 feet. And here's the reason. Even if you have a really long street, there are going to be fire hydrants, there are going to be driveways, and there are going to be no parking zones. And then we will cut streets into basically fewer streets, fewer shorter streets. Right. So yeah, the street length cannot be too long, even if we have a really long street. And also, cars need to be at least 1 foot apart. This is not always true in New York City, but this is just our assumption. And we also consider those good drivers to have a secondary strategy. So it will first try to hit the line, and if it fails, it does the kiss the bumper strategy. And we also make one more small trick is create a smart car zone at the beginning of the street. So it's a place where you have a space, a marked space that's just enough to allow a very small car. So with high compliance, the area will be left open, and in the end, a small car will park there. Okay. Now, under this model, we did some test runs. So in particular, this is a picture where we ran on a street of length 100 feet, and we consider the gap between two markings and how many cars are parked. And here the alpha are the compliance ratios. And one thing to notice is if you pick the length wrong, if you pick the wrong length, it's going to have a very bad effect to how many cars parked, even if the compliance goes to 1. Right? And this is because if you have, for example, if you have a gap that's not large enough, but you have some large cars parking it, then the remaining space is not sufficient to park any other cars. And that is the case where you see a drop in number of cars parked. But if you look at the peak of when you have the most number of cars parked, it's closely, well, it's basically around something higher than the average. So for this, it's around 10 inches higher than the average. And for this, it's around 20 inches higher than the average. And you can see the difference. For example, when alpha its compliance ratio is 50%, so 50% follows the rule, you already get around 5 cars parked compared to if compared to the baseline, it's around 4.6 cars parked. So you get 0.4 cars parked extra. So what it shows is you get 8% for a typical street, and we have a marking for area, let's say 400 inches, and then a compliance ratio of 50%, then the expected number of parked cars would increase by 8%. Yeah, so for more details, there's other more interesting comparisons. You can directly go and see the paper. Thank you.